Yeah. तुम क्या भेज रहे हो सुकन्या को? यू कैन जस्ट सुकन्या नहीं सॉरी उसको पूनम को यू कैन जस्ट कॉल हर एंड टेल हर कि लिंक इज सेंड।
Our nice opportunity that Subhendra Mohanty has come here and talk. He is from research laboratory, Sabah. They have done it in a couple of months. Professor Nanopulas. Nanopulas is big passion. Also, he is collaborator of mine. And after that, he has done his postdoc at ICT PSP. I think all of you know that. And then France, Switzerland. And after that, he came to India, and then he was for some time at Institute of Physics, Bhubaneswar. And then he joined at and he has done over a wide range of things, starting from foundation of quantum mechanics to then cosmology and also to particle physics, astroparticle physics, so over a wide range of interest. And there was sort of overlap with me. I know him for a long time, of course. So there was sort of overlap with me together in the research laboratory. It was quite entertaining to have any discussion with him. So I still remember. Anyway, so that's yeah.
Thank you, Ratil, for that nice introduction, and thank you, Abhish and Ratil, for this invitation to give this talk. So I'm going to talk about gravitational waves. You must have all heard that gravitational waves were discovered at LIGO. And the important thing about gravitational waves is it's a new window in astronomy. Like we have information about stars and galaxies from light, neutrinos, and now from gravitational waves. So the extra window for studying astronomy. But in this talk, what I'm going to talk about is that gravitational waves open a window to nature, the study of the quantum nature of gravity. Now it is well known that this quantum theory of gravity is a very difficult problem. There is no renormalizable theory of which combines which combines gravity with this quantum field theory. Like there is a renormalizable theory of electrodynamics. So electrodynamics has a quantum counterpart, but gravity doesn't. So that's a very difficult problem, how to get a renormalizable theory. But I'm going to talk about something much simpler. And what I'm going to talk about has its parallel in, for instance, light. Around 1900, it was well known that electromagnetic oscillations are what we call light. So oscillating electric magnetic fields are electromagnetic waves, and what was visible light. They were identified as the same thing. But whether the light was a photon or it was a wave was not clear. The photon nature of light was first established actually through statistical mechanics. So Planck gave a radiation law, and
Carry on, please.
so Planck gave a radiation law, a statistical law for describing radiation, and Bose found that if you treat light as quantum, only then you can derive the radiation. So through statistical mechanics, they established that light are come in quanta. Now the similar question is very important in gravity, because gravity, it is not clear that these gravitational waves whether comes in quanta or they are just waves like classical waves, whether there is something called graviton as a counterpart of photon or not, that is a question. And that kind of thing can have some experimental tests, like the photoelectric effect was there for verifying that light comes in quanta. So that is the aspect which I will be touching upon. That whether light, the gravitational waves that we see are quanta or not, that will be what my aim of my talk is. So what I am going to do is treat this thing which has been treated classically as a quantum field theory. So I will derive the thing which I have done classically in a quantum field theory way, and then see whether there is something which tells us that this gravity is in quantized forms or it is better. Okay, so with that introduction, let me start at the beginning. Einstein gave his theory of general relativity in 1916, and he gave this, and So there, the main point of this theory of general relativity, he said that gravity is not like other forces like electromagnetism, but it is like a geometry. So you have to change the metric to describe gravity. And then he says that if you have an oscillating gravitational field, it can propagate in the form of gravitational waves. And he gave this correct formula of what is the energy carried away by gravitational waves, that this is the third derivative of your quadrupole moment, third time derivative, square of that will be the energy carried away by gravitation. So this was a formula which is still used, and this was given by Einstein himself in 19. However, for Einstein, it was actually, in this subject, it was downhill from there, because he was not exactly clear whether these gravitational waves are real or not. See, the main point about gravity was that you can always go to a frame where there is no gravity. For instance, if there is gravity here, you step outside, step on the lift, and let the lift freely fall, the gravity will go away. So if you can always choose a coordinate where you eliminate the force. So Einstein said, well, if there is something oscillating and the gravitational wave is passing, you can go to that oscillating frame, and in that frame there will be no gravity, a gravitational wave. So are they real or not? He had doubts for a very long time. So for instance, he wrote a paper with Rosen in which he showed, he was raising doubts about gravitational waves, whether they are real or they are a gauge artifact. So he submitted this paper to Physical Review. Physical Review sent it to a referee who happens to be Robertson of the Robertson-Walker metric. And the referee said that this derivation is not correct. Einstein himself said that his objections to gravitational waves are not correct. And so the editors of PRD respectfully forwarded it to Einstein, saying that, sir, can you look at the referee report? And this is Einstein's response, that I submitted the paper for publishing, not for sending it to referee. So I'm going to withdraw it. Okay, so he withdrew it, and fortunately for him, it prevented him from writing a wrong paper, because ultimately this paper was wrong and Robertson was right. And later on, he met Einstein, and after a discussion with Robertson, of course, Einstein immediately realized his mistake, and he then came to the right conclusion that there are gravitational waves. What, this one? Yeah, so what Einstein did was he changed his conclusion and sent it to another journal, and that published it. Okay, so Einstein was wrong, and then he actually changed his mind. So that was something. Okay, so as I said, just a brief review, that there is something called the equivalence principle, that if you have a metric, okay, and you expand it around the flat metric, okay, what we call the force equation, Newton's law, the second derivative is the force. In general relativity, is the second derivative is this Christoffel tensor times this product of velocities. This is the force law. And this Christoffel tensor is actually some derivatives of this edge. So you can find out what is the force or the acceleration of a particle from the metric, but you can always go to a frame where this force disappears. But it is Einstein himself had shown that if the second derivative of this what's called the Riemann tensor is real. So what is Riemann tensor? That if you step into the lift, you drop to, let's say, cricket ball, and the lift falls. Okay? Each ball is weightless, and you are weightless. With this, you all falling together. But because of the Earth's gravity, you'll all be moving towards each other because it's radially directed. So the balls will be moving towards. So if you have two adjacent geodesics, there will be a motion between them, and that motion depends upon the fact that metric here and metric here are slightly different. So that's called that the difference between the two metrics is the Riemann tensor. So the point of this whole discussion is that when a gravitational wave passes, you can choose a frame where there are, let's say, two objects, two balls here, okay, and you can choose a frame in which this one stays motionless, so you are basically oscillating with this one, but that one will still oscillate. So you cannot choose a coordinate in which metric disappears everywhere. You can make the coordinates, choose coordinates so that the metric disappears at one point. It becomes flat at one point, not everywhere. So that was the proof that actually gravitational waves exist, that the Riemann tensor is non-zero for gravitational waves. And if you have two particles, they will have a mutual oscillation. Okay, so that is the how. So this is the principle behind the gravitational wave detection also. That if you have a laser interferometer, the mirrors, they will have a motion, just like this ball, and the gravitational waves pass, and that's how they are detected. So just to put it in little bit formulas here, these gravitational waves come in two modes. One is called the plus mode, and one is called the cross mode. So a plus polarization, so if a gravitational wave is passing perpendicular to this screen, it's in the plus polarization. If you have a ring, it will oscillate in time like this. So it makes a plus shape in the way it oscillates. If it's a different polarization, then it will make this shape. In time, this ring will become this oval, then come back to the ring, then oval like that, and so on. So in time, it will look like this. So this is what it looks like cross. The movements are in a cross form. So that's why this is called the plus polarization and this is called the cross polarization. And experimentally, this is how you detect a gravitational wave, that you set up a laser such that the L arm is along here or along the cross direction. And if a gravitational wave passes, the length of the two arms changes, and you will have a gravitational wave. Okay. Now, interestingly, everybody thinks that gravitational waves was detected by LIGO in 2012, so by 2016. There was a big event and everybody heard of LIGO. But gravitational waves were actually discovered not in LIGO, but long back in 90s, early 90s, in a different way. And actually a Nobel Prize was given for the discovery of gravitational waves in 90s itself, maybe I think in 1993. So the way the gravitational waves was detected was indirectly. So what happens here is that you have a binary pulsar. Okay, so you have two pulsars. Pulsars are neutron stars, which are they have axis along which they are beaming radio waves, but their rotation axis is different. So when that beam passes, when they rotate and the beam passes the observer, it appears like there is a pulse. Okay. Now, if you have two of these pulsars and you can observe at least one of them, then you can see the time period of this oscillation. Now, this time period is, in these particular cases, about this, the distance between them is about 1 astronomical unit. So you have two solar mass objects within 1 astronomical unit, and their time period is about 8 hours. So they are rotating around each other about 8 hours time. But in the course of their rotation, this was observed over a period of many years, and this was the time in which atomic clocks were used for measuring time. Now, atomic clocks have at that point had an accuracy of a nanosecond. So they can measure time up to nanosecond accuracy. So what they found was that the time period, okay, of this changes by something like a millionth of a second in a year. Okay, so that goes around, and in a year, the time period changes by millionth of a second for an 8-hour period. But this was possible to do that because they had atomic clocks measuring that. And Hulse and Taylor, these two were the first to observe this change in the time period. So they measured the time period, and then they realized that the time period, the reason they are losing time period is because they are radiating gravitational waves, and it was following this formula. So this is a very famous formula. This actually uses Einstein's equation, but for this particular binary system. And these are the two masses. This is the major, semi-major axis, eccentricity, and this is the time period, and you plug it in and you'll get this number for the energy rotate. So they you observe the masses and period and everything, and when they put this in, they found that this Einstein formula was being obeyed to about 1%. So this gravitational wave, the fact that there are gravitational waves was known, was accepted even in 1993, although most people think that it is a LIGO discovery, but it's not. The Nobel Prize was actually given for this discovery of gravitational waves through binary pulse. So it was acknowledged that they discovered gravitational waves. For Hulse and Taylor. So Taylor was actually the professor whose program it was, and Hulse was the person who was in Chile observing. So he wrote all the time period in his notebook. And within 2 or 3 years, he quit the field and he was working in the industry. Till he got a call from the Nobel Committee that he have got a Nobel Prize. So Hulse had a good ride. He just did one thing and that was the other one.
Gravitational waves were not detected per se, but
Yes. Yeah, was observed. Which established Einstein's formula and thoroughly. So this is over the years, you see, from 1975, that's when he started observing, till 1993 when he got the Nobel Prize. They measured the time period. So these are the dots, and this is the prediction of GR, and it is following exactly. So the Nobel Prize was given, and that's it. Okay. Now is another way in gravitational waves were discovered, that is for merger of black holes. So when the black holes rotate around each other, they come. So this is after many millions of years, after they are very close to each other. In the last about few seconds, about 10 seconds, they come so close to each other. So the amplitude of the gravitational wave is so high that when it carries across, it can move the mirrors on the earth here and be detected. So this is a direct detection of gravitational waves, and that was what LIGO discovered. So this is in the last stages of merger of black holes or even neutron stars. So there are two detectors, Hanford and Livingston. They detected signals independently. They are about 3,000 miles apart in US. So one is in north, one is south. The gravitational wave passes, and it takes some nanoseconds to reach from here to there, because it travels at the speed of light. So there is an offset in the time. So when you account for the nanosecond offset, these two signals superimpose and you get the gravitational wave. So that was two independent observatories that discovered the same signal with a small offset in time. Now we'll come to what I'm going to talk about, the field theory of gravitational waves. So the basic idea of field theory is the following, that all of you know Coulomb potential. You have two charges, there is a force of attraction between them, this is Coulomb's law. But if you talk about quantum electrodynamics, how you think of this is that you have an electron that has a world line. So this is the position, this is time. World line is this. You have another electron who follows another wavelength. So what it does, one electron emits a photon and it gets absorbed. This is not a real photon, this is actually what's called a virtual photon. It exists for a very short time. Within that time you can break energy momentum, so it actually carries zero energy but some momentum. So what this photon exchange of photon does is that there is a repulsion between this electron and that electron. So that is the concept of force in quantum field theory. So what we do in quantum field theory is we calculate what's called the probability amplitude. We take this diagram, or this is called a Feynman diagram. For each of these vertices, we put a coupling constant. So this coupling constant is E. For the electron, E is 0.3. E square upon 4 pi is what's 1 by 137. So what we call charge in classical theory is actually just a coupling constant. Coupling constant means the probability of photon coupling to it. And we put the propagator for this particle 1 by k square, and that's your probability amplitude. So this has a probability of this square of this is the probability of this thing taking place, and from this you can calculate the scattering amplitude. However, classically you can think of it, if you take its Fourier transform of this object, that's your Coulomb potential. So what we call Coulomb potential is actually at the quantum level an exchange of a photon, and there is a prescribed formula for deriving these things, and it's called the Feynman diagram. And this is a very well established subject of quantum field theory, that you do processes through Feynman diagrams. Now, in this talk, I will be talking about the same thing. So, what we did was, just like charge, you have the stress tensor, energy momentum tensor of your binary. This is 2-star binary system, and it is represented by this line. And at some point, it emits a gravitational wave, or the graviton. This gravitational wave travels from the star to Earth, and here it is changing the arms of the detectors, that is the size, the length of the arms of the detector, and you detect it. So this process actually conceptually is no different from this process. Although we don't think of it like that, we think of it as some classical radiation coming, and but it is one Feynman diagram with very long baseline. So if we think of it as a Feynman diagram and a quantum field process, we can calculate this. We try to calculate the energy loss in a Feynman diagram way, not through Einstein's formula. So I will not go into all the mathematics here. I'll just tell you the basic. What?
Just like scattering kind of system here also.
Well, the difference is in Coulomb, it's a virtual photon. Here it's a real graviton. So it can go as much as possible, and because a virtual photon will have a very short distance. Okay? Because it's not on shell.
But why you think on shell?
Because here this one is like a dipole radiation. Supposing you oscillate a dipole, it is just a Bremsstrahlung. So this is more like a Bremsstrahlung than a Coulomb. Okay. See, one charge passes the nucleus. There is acceleration. Due to the acceleration, it emits a photon. That is the Bremsstrahlung. Same way with the 2 stars. One star passes another star, it accelerates, and then it emits the graviton. Huh? Real graviton. So the equivalence is not the Coulomb, but the Bremsstrahlung. So we just said that, okay, we know the coupling. Kappa is this square root of 32 pi g, the g being the Newton constant. We need a coupling constant, and we need so we have to describe this stress tensor. The stress tensor is just the reduced mass of the 2 balls multiplied by the 4 velocities. Okay? And it's quite complicated that you calculate these 4 velocities for the Kepler object. But those are details of calculation. But conceptually, we are doing the same thing what we do for electrodynamics. That there is a current and then there is a photon. And if you have done quantum field theory, you will recognize that the probability amplitude is the square of this vertex, okay, times the energy momentum tensor, energy momentum conservation, times the phase space for this outgoing particle, which is the outgoing graviton. Okay, so this is the basic rule for quantum calculation. So we do this for this particular process, and in this we have to square this. When you square this, you will need the square of. So we need this completeness relation, just like we do for photons. Here we use the completeness relation for gravitons. Okay, and here basically I have described how to calculate that completeness relation. That you calculate the propagator of the graviton, and the coefficient of the propagator is the complete polarization. So this follows just like what we do in electrodynamics. So we plug in all the formula, so I don't have to go through this. So what is interesting is that the energy momentum tensor comes out in a little complicated. This thing is Bessel functions, because you have this elliptical orbit. Its Fourier transform is complicated. Normally in particle physics we have plane waves. We just have free particles which scatter. So they have just e to the power ikx type of formula, but here, because you have bound states, it's more difficult, but you just follow the rules and calculate the energy momentum tensor in frequency space and plug that in and then plug in this formula for that energy release. And after doing a lot of algebra, we find that this gives us the same formula that was obtained by Peter and Matthews from classical general relativity. So this is done by myself and Prafulla Panda. This was in 1996. So this was aimed towards this Hulse-Taylor binary. That was the discovery then. So we were trying to say that we can explain that in quantum field theory language. Now experts in quantum field theory know that any calculation in which there are no loops, quantum loops, a tree-level calculation always gives you the classical effect. So we were also not expecting anything different from the classical effect. So this is not a proof of quantum theory of gravity. This is just saying that, well, this language works at least in the tree-level processes, but we do not know what will happen in the loops. But the language agrees as far as the tree-level process. The formalism matches. So that was reassuring that you can do these calculations using quantum field theory. But still, we would like to know what is the proof that this graviton is a quantum. Then we also worked out if you have other radiation like scalar or vector particles, what would the energy loss, and that energy loss will give you the loss in the time period. And you can probe what are the other particles which are interacting with the first one, light particles. So this formalism of using Feynman diagrams was powerful, that you can generalize it to other particles with your gravitons for this current of for this binary pulsar. So basically the point of these calculations was that you are using quantum field theories for calculating processes of macroscopic objects, and it works. And so we got some bounds for couplings and masses. Okay.
The calculation into at this time.
Yes.
What will graviton?
Yes. So that is what happens, that in these processes we think of gravity as an expansion of the metric to the linear order. So you have flat space, and whatever is extra, that is called the graviton or the gravitational wave.
Temperature is resetting by constant gravity.
If you have, for instance, if you can again do this calculation, but for Robertson-Walker background. Suppose you have a Robertson-Walker background, so you have to take the background as a Robertson-Walker and then perturbation on top of that. That can also be done. So then we have factors of 1 over a. Some changes. That as the universe expands, there is a 1 over a suppression in the amplitude of the gravitational at cosmological distance. That is also possible.
Quantum mechanics is about like
They come out saying yes. There are two linear polarizations, but you can think of them. A linear combination, just like you have two linear combinations of light, and then you have circular polarization. So you can think of it as a linear combination of two circular polarization states also, plus and minus polarized light. It's a helicity 2.
so this particular angular momentum speeds have been observed in light also.
Yes. Yeah, they have been observed in light also. So these can also be looked at as a combination of two different circularly polarized gravitational. Okay, so this was the point was that here we can do this for other particles also, which we did. Now, am I going too fast? All right. Okay. All right. I skipped all the mathematics. I thought that the main point was. Okay, now there's something also interesting which is called the soft graviton theorem. And recently there's a lot of papers, Ashok Sen and his collaborators are writing papers on that. So without going to maths, I just say what is the soft. So the idea of the soft graviton theorem is that you take any scattering process. So you have a binary pulsar or you have a scattering of two black holes past each other or any kind of process. Okay? You find out the probability of that process to happen just by itself, the scattering taking place or something. And then you say that okay, this is taking place and a graviton is being emitted. What is the probability of this process now? So the soft graviton says that you first calculate this amplitude, which is simple, and then you put one factor here for the graviton, and that works. So the soft graviton is that you take this an plus 1 amplitude, is this an amplitude times this q is the momentum of the graviton, which is this thing, and pa is the momentum of the ath particle in the amplitude. So calculation of a gravitational wave radiation from an object is actually simplified using this technique. That first you calculate the scattering process by itself, and then you attach a Bremsstrahl's leg. So this is the same thing what people use in soft photon theorems and so on. So computationally, this is very interesting that you can use this technique to make the calculation of gravitational waves from astronomical objects simpler. And I've explained this, but it will take too long to derive this, so I'll just skip the derivation, but this is the result. Okay. Now, what is interesting in this soft graviton theorem is, from this soft graviton theorem, when they calculated the gravitational radiation, they discovered something interesting. What they found out was in certain cases, for instance, when we have a hyperbolic orbit, normally we have an elliptical orbit, something is going around the Earth. A hyperbolic orbit is that like a comet, it goes, turns around and goes away. So this happens a lot. For instance, in our galaxy, we have a 10 to the 6 solar mass black hole, and many other stars are going around it in a hyperbolic orbit, just like comets in our sun. And they are radiating gravitational waves, and the efforts are there that can we detect those gravitational waves. They are coming from the hyperbolic orbit. So what is interesting in this is that in this, you see, this is just the strain. The change in the arm length of one arm of your interferometer with time. So when a gravitational wave passes, we know that there are oscillations in the arm length. So these oscillations are seen. Okay. Now, here what is seen is that after the oscillation passes, the detectors do not come to the same place, but there is a permanent shift in the detector. So that is called a memory effect. There is a DC signal inside the oscillation. And the DC signal is because your initial scattering is also a scattering in which the initial state and final state are totally different. So there is a change. Whereas in the binary, they keep coming back to the same place. So it's oscillatory, true oscillatory signal. Whereas there it's not oscillatory signal. So because of that, there is a non-oscillatory feature here. So what is expected is that a gravitational wave passes, the arms oscillate, but they don't come back to the same place. There is a permanent shift here. So that would be something interesting, that a permanent shift in the arms because the gravitational wave has passed. Permanent shift in the space time. So this is what's called the memory effect in gravity, and people are trying to detect them. Okay, so last no, it is more for calculational simplicity, but only through that this memory effect was proved thoroughly. That so it was useful for proving things which are not done in the general relativity method. So you can now higher order the general relativity using the soft graviton theorem more easily. And so people didn't do those calculations in GR, which are now done in soft graviton theorem. Because yeah, so what happens is that you think of it as a electromagnetic. There is a proton, an electron goes by in a hyperbolic orbit. So there will be brainstorm of photons. These photons are oscillations in space-time, electromagnetic wave. So those are the oscillations which will carry. Okay, so those are the oscillations which we are talking about, not the oscillations of this. Okay. But those photons, if there was a memory effect, they will oscillate some charge here. But what happens in gravity is that the oscillations do not die out at the same place. There is a permanent shift. So that is the remarkable new feature that you'll see in this. Yeah, so it is not related to the fact that this is changing, but it just happens that in the non-hyperbolic in the elliptical orbit there is no memory effect. That's okay. So here I'll just go back to one paper we wrote many years back for the inflaton. So in another place where we predict that these gravitons behave like quanta are in the early universe, which are during inflation. So what we expect is that there was a 0-point energy of gravitons, which we should see now as gravitational waves in the background. Just like there is a 3-degree photon in the background, and people are trying to discover that through the CMB. It's called trying to look at the B mode polarization. So the 0-point energy of graviton, if they see, that would be excellent test that these are gravitons actually are the gravitational waves are actually gravitons. However, B modes have not yet been seen. In this paper, what we did was we said, well, supposing that this factor of half is this half h cross omega for 0-point energy. You must have read about 0-point energy. Supposing this bosons have an interesting property that if there is an emission of boson from a system into a background in which there are already bosons, then this process is enhanced. Okay, this is called a Bose stimulated emission or a Bose enhancement. Okay. So if there is a background of a thermal graviton, so there is a just like 3-degree background, there is a thermal background here, and if you have a 0-point energy, then you should see together, and this factor is caught hyperbolic. So instead of heart, you'll have this thing, and there is an enhancement by this factor in your B mode. Yeah, and inflation it is all field theory calculation. In inflation, both the inflaton and this is just a field theory. There is no classical. But this inflation part has not been seen. The gravitational waves which are seen, binary, those are all classical calculations. So classical calculations have been tested experimentally. Quantum calculations have not yet been tested. So, so we said there will be this enhancement factor if there is this factor, and this, I mean, this is still there. That is in the signal you should have this enhancement factor in the beginning. So why I bring that up now is that if there is a similar stimulated emission of gravitons from binary pulsars or black holes. So now I am saying that if there is a radiation and in the background there is already a background of gravitons because of this inflation or like the thermal background, then emission of the graviton is enhanced by this extra factor, and this comes out very simply. If you take, zero state, you take thermal state. When you calculation, you will get this extra factor. So we are saying that if you have this, then you have this similar enhancement factor, which will show up both in LIGO signals as well as this binary pulsar. And what is important there is that this particular factor, this is the Bose distribution, and Bose distribution is a signal that the particle you are dealing with is a quanta. So this comes from the assumption that those bosons are come in quanta. You have one boson, two boson, n boson states. So this particular thing would be a proof that your gravity, what we call gravitational fields, are actually gravitons. Just like we use electromagnetic field with a photon. Huh?
It's only boson.
No, no, but quanta of boson.
And quanta of boson.
Yeah, that is all.
Graviton is something more.
No, no, that's all we mean by gravity, graviton. That is the gravitational wave a quanta. Now, whether there is a quantum theory of gravity and what is that is a renormalizable is a big question. That is also sense. What we are saying is, can we detect a graviton? What is the signal that this is a quanta? So that is all we are saying. This will not point towards, what is the gravitational, what is the quantum theory of gravity? We don't know that. Huh? Much later, yeah. Quantum theory of light came much later, right? QED. But the idea of photon was in 1900. Einstein established that. So similar thing. We are at that stage right now for gravitational wave, or at least I'm doing good things at that stage. But there are people, of course, you know that this research is being carried out all stages. Okay, so that brings me to the end of my talk. That this is what I'm doing right now. That I'm working out the signals for what will happen if there is a graviton, what says it is a continuous thing in the both the binary system as well as the LIGO system. So that's fantastic. Thank you. So I skipped a lot. You can ask questions.
The background is classical.
What?
The background is classical.
Background means we are talking about the source is background. So for instance, this calculation is like we have a heavy object, charged object which is accelerating and emitting electromagnetic wave. You can carry out that calculation also using field theory. But treat this background object as a classical object. It means that background object doesn't have a creation annihilation. It is always there. Whereas the photon has a creation annihilation and so similar spirit we are doing. The stars we are thinking of as classical object, but the graviton we are treating as a quantum object.
The H new part is the graviton.
Yes.
Which is moving in flat or orbit, or whatever metric they consider.
Yeah, it can be both flat metric, eta mu, or it can also be in the Robertson, any other kind of metric. So that H mu part we are treating as a quantum.
That is likely to be that would
Yeah. Which?
Aspiration that one of that.
Yeah, that can be because of a black hole. It can be another neutron star, and anything. So gravitational waves have been seen from two black holes, one black hole, one neutron star, and two neutron stars. All combinations have been seen.
There is the motion of that will be that would
Well, GR will be used only at the coalescence stage when they start merging. Okay, when they are two short-shared radius overlap, then GR becomes important. But in the last, that is in the last second or so. Till that time, the Newtonian dynamics of two objects, because gravity beyond the short-shared radius is still Newtonian. So this calculation is good till the last stage is the coalescence stage. So here in this language, instead of using linearized gravity, you have to take higher order in the graviton emission, because you are now dealing in strong field region, not in the weak field region. Yeah. So the GR basically is coming. So in the quantum theory of gravity, just like in electrodynamics, you have a coupling of the charge, the photon A mu times J mu. J mu is the current, and the current can be made of elementary particles or it can be a classical current, anything. So J mu mu is the basic coupling. Similarly here, T mu nu, epsilon mu nu. Epsilon mu nu is the coefficient of H mu nu. This is the polarization of the H mu nu. Yeah, that's the polarization of the H mu nu. That is the basic coupling. That comes from the Lagrangian.
And this,
After that, we are not using GR at all. After that, we are using the rules of quantum field theory. That if you have a coupling between a T mu nu and a G mu nu, and I know from the background motion that the just
starting point, but like
that's it, yeah. After that, we are dropped GR.
we are not doing, we are not considering any.
Yes, we are not running any dynamics. We are just taking the coupling from the theory.
So does anybody have any questions? People who are online? I believe none.
Okay.
So if there are no further questions,
Thank you.